So we will be talking about quantum key distribution. We'll see what it means, and then we will talk about a idealized simple protocol, and then we will talk about how you process those data. So in terms of outline, okay, I have, so, but before we can get into the details of a QKD system, I would briefly talk about classical cryptography, because many of the students probably coming from different backgrounds, and it would be useful to know what cryptography means and what the QKD adds to the scenario of cryptography. So to begin with, cryptography is a study and practice of secure communication. Now, what is a secure communication? There are actually two primary things that consists of secure communication. First, you need authenticity of any message that is sent. So you have received a SMS or email, you want to make sure that it is coming from the correct person. So it's not a scam SMS. So that's the authenticity. And then there is the other kind of security. It's called the secrecy. So you are sending an email to another person, a business email, and you don't want any rival businesses to read your email while it is passing through the internet. So that is the secrecy, which comes from the encryption. So in this talk, we will be mostly talking about the secrecy of the messages that encryption protocols provide. So how does a encryption protocol looks like? In encryption, you want to encrypt some message, some plain text message, email, or your password, your credit card number. We call it M. And then you need an encryption key, which is the like password for the encryption. And then what you want to compute is a ciphertext. And for that, you need an encoding algorithm. So here the enc is the encoding algorithm. You input your message and your key into this encoding function. It spits out the ciphertext, and there is a decoding function. So you send this ciphertext over the internet to the remote party, and to decode these matches, the remote party uses the decrypt algorithm and then decrypts it. So how does it work? So let's assume we have Alice and Bob, and Alice wants to send some message M to Bob. She computes the ciphertext C using the encoder function and sends this C over the internet or over any network to Bob. Now this encoder function is such that nobody can break it without knowing the key. However, Bob already knows the key, so he puts that key and the ciphertext into his decrypt function, and then he recovers the message. Now, what are some examples of the encryption? These have been, encryptions have been used for thousands of years. For example, Julius Caesar used to use a Caesar cipher, which is very simple, where you have a message and then you shift each letters 3 steps towards left. So what you do is, for example, you have a message that I like tea, and then you want to encode it. What you do is you replace I with F. F is F, G, H, I. So 3 steps GHI, 3 steps previous to the current letter. So all the letter are replaced by 3 letter previously, third letter to the left. So if you replace all those letters like that, you get the ciphertext, and this ciphertext looks like quite unreadable. However, if you know the key that, okay, all the letters are shifted by 3 positions, then you can recover it. You can just take all the letters and then replace by 3 letter from on your right, and you will get the original message. However, this kind of protocols are very insecure, because even if you did not know the key, you could try all the 26 letters or shift positions, and eventually you will find a shift where everything gets decrypted. Now one can, instead of having a shift, one can replace all the characters by arbitrary symbols, or they can have different character having different kind of shifts. But all those protocols that have been used historically are actually insecure, so a modern crypto analyst would be able to decipher them in seconds. So what do we use currently to do all the secure communication? It is called AES, Advanced Encryption Standard. So that is, in AES cryptography, you still um, have a key, and then you can encrypt as much data as you wish. You can encrypt a whole movie of gigabytes of size. It doesn't matter. It will just encrypt everything. But then to decrypt, you will need the key. So key means, let's assume you have a password. You have some 20-digit password or 10-digit password, and you have encrypted a gigabytes of data. Now, how do you break this algorithm? You could potentially try a brute force attack where you try all possible 20-digit letters and numbers, and then try to decrypt them using that number one by one, and you see when the decryption successfully happens. For example, each movie will if you look at the file, if you open the raw file, you will see that initially, if it's a mp like 4 format, you will see that has a known header. There will be like some text that is always the same. And then what you can do is you try this new password, you guess randomly a certain password, and you decrypt that initial part and see whether that initial text is getting recovered correctly. If that happens, you know that you have found the raw key, like the secret key. However, this is very time consuming. If you, even for a 20 bit sorry 20 digit password, has in binary, it is says 8 characters, so 20 times 8, 160 bit, 160-bit password, and you will need all 2 to the power 160-bit possible guesses to attack it in brute force, which is extremely time consuming. It will actually exceed the life of the universe. So that way it remains safe. However, there are certain quantum algorithms that can reduce this search space by half. So that way, sometime quantum algorithm can help you attack this kind of protocols. But then again, to decrypt a huge cipher text, you only need to guess the password or the key, which is a very small in comparison to the size. So you, and also then if you have this AES algorithm, one clever person might in future find a way to break it just without knowing the password, because they know the function. These functions are known. They might find a certain inverse function that will allow them to just decrypt the AES function. So then the question is there a protocol or is there a cipher that cannot be broken, even if you uh, like which is equivalent to guessing the whole message? For example, for AES, you just need to guess the um, password or the key, but you don't need to guess the whole message. But can there be a protocol that can actually force you to guess the whole message instead of just like password? So yes, there is, which is called a one-time pad or Varnam cipher. So this cipher is constructed with a Boolean operation called XOR. You might already know this. So XOR happens on two Boolean numbers, 0 or 1, and say A and B are these Boolean numbers. If A and B are same, then their XOR is 0, and if they are different, their XOR is 1. Now, how do you compute? For example, if you have a message which is 1011, I'm just taking a binary message for simplicity, because any text eventually gets converted to binary. And for this, you need a key or password or key, which is the same length as the message. So you have a four length message, you need a 4 length key. And how do you compute? You perform a bitwise XOR of the key and the message. Simple as that. So for example, on the right, we have this message on top, and in the middle, there is this key. And we have computed the cipher in red. So for example, in the first digit, they are different. So the output is 1. Second digit, they're different, 1. Third digit, they're the same. So the output is 0, and so on. So this, to be able to break this Varnam cipher, you need to guess the key. But the key is the same length as the message. So if you can potentially guess the key, you can also guess the message directly. So it means if you have a gigabytes of numbers or message or cipher that you want to decrypt, you need a key which is gigabyte length, and then you need to guess all these bits correctly, which is now even, so it's 2 to the power these gigabytes of bits. So that's like a number we cannot even imagine. So this way, the Varnam cipher is secure, and we call it information theoretically secure because to guess its password is equivalent to guessing its content. That way, it is completely secure. Now, in all the examples that we saw, we had both encryption and decryption keys were same. However, there are this asymmetric key cryptography where you have a message and you encode the message with a encryption key, and then you decode the message using a decryption key. For example, here Alice has an encryption key KA and Bob has a decryption key KB. And these KA and KB are related. So they are not arbitrarily chosen. They are related, and the protocols and the keys are chosen in such a way that Alice can encode it using KA, but even if she exposes the key, nobody will be able to decrypt it unless they have the decryption key. So because in this case, the keys are different, we call it asymmetric cryptography. Now, there is this asymmetric, what do you use this asymmetric key? It's in the public key infrastructure. For example, if you open Google from any device, you will see that the web address has HTTPS, and then there's this lock sign in all the modern, or the shield sign in all the modern browsers. It means the communication is secure. Whatever you are searching, nobody can eavesdrop. The government cannot, even your internet service provider who actually handles the data, they will also be unable to see what are you searching. Only Google will be able to see this. However, you have never went to Google, you have never established any key with them, right? You never visited Google and then took a pen drive and installed a private key there. You have a password, of course, but then when you even started, even without password, if you log out from your Google, if you just open a browser, fresh browser, and if you start searching, you will still see this HTTPS. It means the communication is already secure, even before giving any password or anything. So then what's happening? In Google, the password that we provide is not for encryption, it is for authentication. So by giving the password, we prove to Google that I am the person accessing my email account. The encryption happens independently using the public key infrastructure. So how that happens? For example, all the major service providers, Amazon, Google, Facebook, Lazada, even if you also open a website for yourself and you want a secure website, you will also have to register yourself with this public key infrastructure. And then what this infrastructure will give you, or actually ask you to, there are certain protocols, they will ask you to generate a public key and a secret key, and you will secretly generate it. For example, Amazon, Google, Facebook, all of them has done it. Maybe a few of their people knows. So they generate this public key and secret key. They keep the secret key to themselves, keep it as a like an official secret, very important. And then they publish the public key to this public key infrastructure. So if you go to the Google, if you just search online, you will be able to see all the public keys of all the known websites that uses secure communication. So now if you want to search Amazon, if you want to search Google, you don't have to do anything because the browsers already have it installed. They internally do take care of all these things. So if you type Google, what the browser does is it looks up the public key of Google, and then using that public key, if you are searching for, say, quantum, and then they will take that message, which is quantum, they will use the public key and encrypt the quantum using the encryption key, and then they send it to compute the cipher and send it to uh, Google. And Google will decrypt the message using their secret key, and then they will be able to read the message. Now, how this system works is by using the public key, you can only encode, but you need the secret key to decode. Now, what are the algorithm that is actually used in practice? So one of the algorithm is called RSA. It's the initial of the authors, which I don't remember at this moment, but it's a very famous protocol. In fact, all the secure communication in the world, public key based, uses RSA. Anytime you make a credit card payment or log into your website, Facebook, or email address, it uses RSA. So how it works is the website who wants to publish their public and private key, they generate two prime numbers secretly, P1 and P2, and these prime numbers are very large. They have thousands of digits, and then they multiply these two numbers. So if each one had 1,000 digits, their multiplication would have a 2,000 digit length, and it will look like a big number without, I don't know, without any pattern. To be able to factor it, you will have to search this 1,000 digit numbers. You like divide one by one or use some advanced algorithm, and one can show that even the best known algorithm to factor these 2,000 bit numbers will take like thousands of years with modern computer. So that way it is impossible without knowing P1 to figure out what is the P2. So what happens here is this multiplication, after the multiplication, the number you get, that becomes the public key, and the secret key is P1. And if you know P1, it's very easy to know P2 because you can just divide and you will know what is the P2. But computationally, it's very difficult to get P2 from just the multiplied number. However, quantum computers can easily factorize these numbers. So therefore, quantum computer is also a big threat to the public key infrastructure. And what can happen is once a proper big quantum computer is built, all the communication that we are currently doing will become vulnerable. Now, how does the public key crypto system work? Do we every time, when we type a password or do like download my email or some image, like megabytes of image from my Google Photos, do they do all this 1,000 digit multiplication with all the bits? No, because that would be, again, a very computationally intensive task. All our laptops or mobile phone would be like overworked. So how does it work is using the RSA, initially my browser would generate a random number secretly, locally, maybe a 256 bit random number. And then using the RSA, using the public key of Google, it will send this random number to Google. And because it's using RSA, nobody can decrypt it. So Google can use it using their private key, decrypt the R. And from then on, all the communication that we perform will use R as the key. So the newly generated R. And then for this, they use the AES algorithm, which is very fast and efficient, that we talked about previously. So after the initial stage of public key protocol, in the next stage, they use the symmetric key protocol, and which is very fast and efficient. So now the task of QKD, because we know that RSA can be broken by quantum computers, then this initial password exchange, initial exchange of this raw key or this R, that needs to be solved. How do we do it without having a secure public key system? Here comes the quantum key distribution. So quantum key distribution itself is a quantum proof. So you cannot, using a quantum computer, break QKD. So that's the benefit. So this quantum is its own disease and its own cure, in a sense. So we use QKD to do that. We'll see how these QKD protocols work. Okay, I think we have time. So the first, this type of protocol was proposed or actually published by Bennett and Brassard in 1984. And this protocol is nicknamed BB84 from their initials and the time. This particular protocol is called a prepare and measure type protocol. You might have already, from your exposure to quantum mechanics in the last few lectures, you know that quantum states can be prepared, and there is such a thing called measuring the quantum states. So in this BB84 protocol, Alice prepares various quantum states, and she also writes down which state she prepared, and then sends this prepared message, qubits, to Bob. Here qubits can be photons, so it could be just photons traveling through optical fiber or free space. And Bob then measures them, but by measuring in quantum mechanics, you have to, it's not enough to say that Bob measures them. You have to tell in which basis you measure. So a same qubit, if you measure in different bases, you might get different outcome. Therefore, Bob has certain possibilities of choosing which basis to measure. So he randomly chooses those bases and he measures the outcome. And eventually, from the Bob's measurement outcome, his measurement choice, and Alice's preparation information, from this information, you can actually establish a secret key. So we will see how that is done. The other kind of protocol uses entanglement. This is developed by Arthur Eckert in 1991. Eckert was a director of our Center for Quantum Technologies, and he is still a researcher here, but our director has changed. However, this protocol uses entangled photons, where some source prepares a pair of entangled photon and sends one photon to Alice and another photon to Bob, and both Alice and Bob then perform some measurements and they communicate to each other to perform QKD. And actually there are quite a few other QKD protocols, but they are different flavors of these two type of protocol. One is the prepare measure and one is entanglement based. All the protocols can be actually traced back to these two roots. However, in this particular talk, we will only be talking about BB84 type protocol. So let's see how QKD steps work. So you will have Alice preparing some state, sending to Bob, and then there would be some quantum communication. However, these photons will have some delay over the transmission, and there will be some missing photons because it will be absorbed in the medium, and there will be some additional stray lights going into Bob's detector, and then they will have additional events. So there will be a lot of error. So what they will perform next is some kind of coincidence matching. So they have to compute the delay, propagation delay, and then they have to find that, okay, whenever Alice is creating a photon, am I receiving a photon at that window? Considering the propagation delay. If I receive something there, I call it a match. So it means I am receiving something that Alice has sent. But if I receive something at a different window, I could say that, oh, okay, this is a stray light. Of course, there is still a possibility that the stray light will come into the same window, and that will introduce some error. We'll see how that is handled later. So what they do is, after measuring, they do something called basis reconciliation. We will see how it is done. And after that, they have Alice and Bob have shifted keys. They perform something called information reconciliation and then privacy amplification. and then the output, Alice outputs key Ka, Bob outputs Kb. However, if the protocol is correct, then Ka is equal to Kb. So in this protocol, we can see that by just running this protocol, Alice and Bob were able to establish secret key between them, and we are not using any prime factorization, which is broken. Now, we will look at a very idealized version of BB84, but you have to understand that there are additional technical and theoretical challenges when you actually implement it. So how does it work? Let's assume that Alice prepares her photons in 4 different polarization states. I am not putting any Kate sign here, but let's assume that these states are denoted H, V, D, and A. So where H means a photon that is horizontally polarized, and this is denoted by this horizontal vector. V is the vertically polarized photon. D is the polarization, which is the sum of the weighted sum of the H and V. If you add these two vector, you get D. And then if you subtract these two vector, like H minus V, you get A. So that is another photon, which is 45 degree, but it is exactly 90 degree to the D. Now I have this blue and orange lines. They denote 2 different bases. So you have HV basis. So if you prepare some photon in H and you measure in the HV basis, you will always get outcome H. But if you prepare a photon in H, a photon H, but you measure in DA basis, which is 45 degree apart, you will randomly sometime get outcome D and sometime get outcome A. And there is no pattern in it, it's completely random. And same to the V and D. So to get the right outcome, you have to always choose the right basis. So if in whichever basis you prepare the particular photon, if you measure in the same basis, you will always recover the photon's identity. On top of it, because we will not be using photons to do the eventual cryptography, we will need classical bits or C bits. So what we do is we use some encoding. So in every time Alice sends a horizontal photon, she records a 0, that I am sending a 0. And then anytime she sends V, she records 1. Similarly, when she sends D, she again records 0. And then A, she records 1. So when you look at 0 and 1 on the right side, you don't know whether it's coming from the ASV basis or AD basis. You just know that, oh, okay, it's 1 or 0. And that's that. So for example, if Alice sends photon which are DHHVA, and if you use this translation table, you will know that her raw key is like this, 00011. Now Bob will perform the measurement, and from the quantum mechanics we know that he needs to, if a photon is prepared in HV, any of the H and V, he needs to explicitly measure in the HV basis to correctly recover it. However, he doesn't know, because when the photon comes, it doesn't tell you which basis it is originally created. So what he does is every time he receives a photon, he arbitrarily chooses between HV or DA basis in these two setup, and he performs the measurement. Now, there is 50% probability that he will choose the basis correctly. So the original message was prepared in HV and he has measured in HV. That's 50% chance. And if that is the case, he will recover the message absolutely correctly. However, if there is a if he mismatch, then he will denote it, say I am sending H and you measure it in DA basis, you will get one of D or A as outcome, and it will be wrong. But then again, we'll see that after the translation, because DA will again get translated to 0 or 1, so there is a 50% chance that you will again correctly get the raw key. So for example, here Bob has measured in this all his photons, and he, whatever he choose, he got outcome VHDAV, and if he translates that, he gets his raw key, which is 10010. Now Alice communicates to Bob her basis information. So Alice has prepared all the photon in some HV or AD basis. She will not tell whether she sent H or V individually, but she will say that, oh, this photon I have prepared in one of the H or V, and this photon I have prepared in one of DA. So she will send those messages to Bob. And from that, Bob will know when he has prepared it, measured it correctly. So if he has measured the message, which is same as the in the same basis as Alice has prepared it, he will keep it. And if they have a mismatched basis, then Bob will discard the those events where he measured in wrong basis. Now he will also inform Alice that, oh, okay, these are the photons that I have measured in wrong basis, so please discard them. And after that, they will have a shifted key. Now, even before the shifting, if we look at before discarding, how much error will this protocol introduce? We know that 50% time Bob measures in the correct basis and 50% time he measures in the incorrect basis. So when Bob measures in the correct basis, he will definitely get the right outcome. But um, when he measures in the incorrect basis, again he will have a uncorrelated outcome, but then he will assign 0 or 1 to that message, which is random. So there will be again a half of the time this 0 and 1 will get matched to Alice's 0 and 1. So there will be actually 25% chance that Bob will get it correctly. So overall, you will see that there is a 70% chance that even though Bob is randomly choosing the basis, he will get his raw key will match to Alice. So if they have 100 bits, 75 bits will be matching on average. Now, okay, so now we have two raw key which are 75% correct. And if we do a shifting, we will rule out all the mismatched bases and we will have kind of 100% correct raw key, assuming there are no error in the channel. But what happens if Eve tries to eavesdrop? So how can she do it? There is a photon passing from Alice to Bob, and then Eve wants to know what is the basis or what is the exact photon that is sent to Bob. To do that, she would have to measure it, because in quantum mechanics you cannot do anything. You cannot just observe something like without touching it or performing a measurement operation. So then whenever she tries to measure it or detect it or observe it, she will end up perturbing the qubit. So the qubit will be changed slightly. And then Bob will be able to detect that something is wrong. We'll see how. Now you might say that, okay, why don't she makes a copy of the photon and then sends the original photon to Bob without touching it and then perform the measurement of the copy. But then in quantum mechanics, there is a theorem called a no cloning theorem. It means any unknown qubit cannot be cloned. Uh, and it's a very simple proof. We'll not get into it. Probably you have already covered in the QK quantum mechanics introduction. So these two property of quantum mechanics, one is the no cloning, and then other is no observation without disturbing the state. This gives you a security, because anytime someone wants to eavesdrop, you will know that your photons are getting disturbed. You will know someone is listening and you will discard those photons. And they cannot observe without discarding, because they cannot make a copy and separately measure it, because copying is not allowed. So what Alice can do is she can perform an intercept resend type attack. Intercept resend means what she will do, Eve will do, is she will sit in the middle, receive all the photon coming from Alice, measure them randomly in her own chosen basis, randomly chosen basis, and then send Bob the outcomes. So if she chooses some basis, gets some outcome, like if Alice sends a H photon, but she doesn't know, she measures in a DA basis, she will get D or A as the outcome. And then whatever she gets, if she gets A, she will send A to Bob. So even though Alice is sending H, Bob will receive A. Can this fool Bob? So we can see how this works. We know that 50% of the time, Bob and Alice chooses the right basis. And in the end of the protocol, Bob communicates his basis choices, or Alice communicates her basis choices to Bob. And they discard all the mismatched bases. Now, if there was no eavesdropper, then this 50% of the remaining bits would always completely match. However, Eve, when she performs her measurement, doesn't know what basis Alice has chosen. So Eve will, among this chosen 50%, half of the time Eve will also measure it in the wrong basis. And by measuring it the wrong basis, she will end up preparing a wrong kind of photon and sending to Bob. So Alice has sent H, Eve measured in DA basis, and out came A, and Eve will send A to Bob. Now when Bob measures, because Bob and Alice are now measuring in the same basis, so Bob measures this A in the same basis, in the HB basis, he will also again 50% chance he will get a wrong outcome. So that way, if you count all these numbers, you will see that Eve will introduce additional 25% error in the protocol in this particular case. So in the overall raw key, we know that in overall raw key, Alice and Bob has 75% match. But then if there is a eavesdropper, you will see that the match ratio decreases. So they will have, instead of 70%, they will have 60%, 50%, depending on how much measurement Eve is performing. So they will see that this ratio, the correctness ratio will decrease. Now, how do they know what is correct? Because after the raw keys are generated, which are maybe millions of bits, they will take a subset, say 100,000 of it, and send to Bob. They will exchange to each other and compare in those part and see what is the error. So to sum it up in pictures, so in an intercept recent attack, if there is a eavesdropper, there will be more than 25% error. If there is no eavesdropper, there will be 25% in raw key, but with eavesdropper, there will be more. And by just exchanging a part of your raw key, Alice and Bob will be able to estimate what is the overall error rate. Now, and once they find that error is more than 25%, they will just discard. They'll say, oh, someone is listening, let's not talk. So that way their security remains intact. Now, this can introduce some kind of denial of service attack, because in the middle where Eve is sitting, she can always choose to do some eavesdropping. And then whenever I'm trying to send something, even though I cannot send it securely, I cannot even send it insecurely, because I will discard the protocol, right? Every time I detect someone in the middle, I will discard the protocol. So therefore, QKD has this particular problem that using this tactics, someone can completely stop you from communicating at all. But this kind of denial of service attack are also valid for classical communication. For example, this is common attack hackers do all the time to these big websites. They will generate arbitrary requests to the website so that the website gets overloaded and the real request never gets served. So those are called the denial of service attack. Now, up to this point, we have seen how you perform the quantum step in your QKD protocol, and then you get the then you get the raw keys, which has 25% error. And then if you do the shifting, where you have only keep the bits where you have the matching basis, you will potentially have 100% matching, because when you have you have chosen the correct basis, you should always get the correct outcome. However, there are always manufacturing defects in your detectors, and the system has some inherent error. You will have noise coming in from outside. So you will always get, even after shifting, there will be some error sometimes. So in the whole password, 100 bits or thousands of bits, you will have some bits that are still wrong. Now, since we are using all these bits in cryptographic protocols, if there is a single bit mismatch, the cipher text can never be decoded, because that's the security requirement. The whole password must completely match, right? Therefore, performing just the shifting and the quantum communication is not enough to establish the shared secret key. You need to do a lot of classical processing on top of it. Namely, you need to perform some kind of error correction protocol to correct the error. For example, here I have a example raw shifted key in Alice and Bob, and the red bits are mismatching. Alice has 1, Bob has 0 at this position, and they need to correct it. Okay, how much time do we have left? Um,
You have about half an hour left.
okay, cool. We have enough time. So, um, so we need to perform this um, kind of error correction protocol on the on these shifted keys. Now, how do you model this error correction protocol? In classical communication, we already have error correction protocols. For example, when we send an email to a remote party, our email, of course, remains secure. On top of it, it never gets changed. When I say something, it doesn't intend, like by mistake introduce some spelling error or changes some text to something else. It never happens, even though there are a lot of noise in the world. When you talk, when you stream music on Spotify on your mobile phone, all this music is coming from on a radio wave, and there are so many noise in in our surrounding. Still, you don't hear any noise in your Spotify music. I mean, if you remember, I don't know how old or young you are, in the old times or even now, if you had this medium wave radio or even FM radio, and if your antennas are not good enough, or even you are in a position where your the environment is noisy, you will hear some noise in it with your song. There will be some hissing sound or some kind of noise. You know that the data that is coming to your listening device is getting corrupted. However, these days we don't hear anything like that, because we are using digital communication. And even though in actual medium there are a lot of error, we use these encoding and decoding protocols to weed out all the errors. So eventually you get very accurate representation of the data that was originally sent to you with almost no error. And to do this, you actually need a model of the channel. Like okay, I have this message. For example, here I can assume that even though these bits are generated using a QKD, I can assume that, oh, if what if this was sent over a radio to Bob, and then there is 1 bit error generated. Can I correct it? Can my device correct this 0 to 1, and then everything is normal? So to do that, we need to model the channel. For example, here we can see that this is a binary symmetric channel, where if you send a 0 bit, there is a Q probability that it will be flipped. And if you send a 1, it will be again Q probability, it will be flipped to 0. And 1 minus Q probability, the bit remains same. Now, what happens is, we call it a binary symmetric channel because we are assuming that the probability for 0 to flip and 1 to flip are the same. It could be different. For example, if you are sending electronic pulse, and every time it's a pulse, there is a 1, and there is no pulse, there's a 0. They might have different characteristics. A pulse might get uh, absorbed in the medium easily and become a 0. But when you send nothing, there is a very low chance that a randomly pulse will come up. So depending on what kind of medium you're using, in reality, you might have different probability of error. So there might be higher chance for 1 to become 0, but lower chance for 0 to become 1. But in ideal case, we assume the binary symmetric channel. And even if you have a asymmetric probability, you can take the highest probability as your for both of them. Like even though 0 has a low probability, you just assume that they have the same and then proceed that way. It should still work because you're taking the lower bound. So how do you, so we saw previously that one bit is getting an error in the this 4-bit message that I saw in the previous slide, but that is not enough. To be more mathematically rigorous, we need to quantify this error, and we do it using Shannon's entropy. And if you do the analysis for the binary symmetric channel, you know that the per bit, the amount of error introduced to the message, or the uncertainty due to this error introduced in the message, is quantified by this HQ, which is the function of q log base 2 minus q log base 2. And this is just the particular function that we use. This was invented by Shannon, Claude Shannon, in 1954. Um, so how would a classical error correction code work? You again have some message, and you uh, create some kind of code. We don't call it cipher because we are not using any key to compute it. You just take the message and you do a encoding to a code word, uh, and then send the code through the noisy channel. The noise will change the code to C prime. However, the Bob has a decoding algorithm, which by looking at the code, he can just recover M. So the encoding is such that you do the, they will be able to recover it. A very easy example is called a repetition code, where instead of sending, if you want to send 0, instead of sending it once, you send it 5 times. 0 0 0 0 0. So then what happens is, even if there is an error in one of the bits, you can take a majority vote of all these 5. You will see that most of the time, from this voting, you will be able to correct the error. Now, in QKD, you cannot use the whole message and encode it into code word and send over to Bob in a classical channel, because we want to have some secrecy. If I have some erroneous message, if Bob has some erroneous message, and we want to correct our error, if I encode my whole message without a key and send it to Bob, we cannot use a key because we yet do not have a key. We are still in the initial stage of the QKD. So if we send this to Bob, and eavesdropper will be able to look at it, and eavesdropper has also access to the decrypt function, so she will be able to decrypt it because there is no key. She will just be able to decrypt what I'm sending to Bob. So in QKD, what we do is a different kind of error correction, which is called a syndrome based. So you have a message which has some error. You compute using some function which is called error correction information on syndrome, and then you send the syndrome from Alice to Bob. And from this syndrome, Bob already has the message because he's part of the QKD after the raw key, which has some error, or the shifted key. He has it, so he will take his erroneous message and the syndrome, and he has a protocol that takes these two input and outputs the original message in. So that way he will be able to correct it. And here you are only sending a syndrome, which is a very small number. So if you have a 1000-bit message, your syndrome would be, say, 15 bits. So you are not exposing a lot. You are only exposing 15 bits worth of information. Now, there are basically two types of error correction protocol. One is a one-way error correction, where just as we saw that Alice computes some kind of syndrome and then sends to Bob. These are example are LDPC and Hamming code. And then there are interactive error correction protocol, where Alice and Bob talks to each other back and forth. Every time they send a very small amount of information to each other, but then they are able to eventually recover their correct their message. So to see how this syndrome computation or this error correction protocol works, we will have to introduce this one uh, notation, which is called a parity. So assume that X is a binary string, consists of zeros and ones. Now, if X contains even number of 1, we call it a even parity and denote by 0. So if parity X equal to 0, I know that the original message had even number of 1. If parity X equal to 1, I know that the original message had odd number of 1. Now, this parity can also be computed using the XOR operation directly. So instead of going through all the bits and counting one by one what are the number of ones, you can just take a Boolean circuit or Boolean equation where you XOR all the bits x1 to xn, and the outcome would be same as the parity. So for example, the parity of this 1011 is 1 because there are odd number of 1. Parity of 1010 is 0 because that is even number of 1. Now we will look at a very interesting protocol called low density parity check code. This was developed in 1960 by Robert G. Gallagher. This was not used until like 2000, I guess, because it is a bit computationally intensive and we did not have good computers or good computing device. And in fact, that is why all our old radio had noise. But these days we have even a small machine, small processor has a very big computing power. So all the FM radio device that we carry or the MP3 players or iPod, iPad, everyone has this kind of LDPC type implementations. So when the actual communication happens, they correct all the error easily. So how this computation is done is the LDPC code is defined by a n by n parity check matrix. And this matrix is publicly known. So both Alice and Bob knows the matrix and everybody knows. Like if you are using a standard LDPC implementation, you will know what matrix they are using. Um, and these matrices are binary matrices. So each of the elements are either 0 or 1. Now, okay, should I go to this detail? Okay. So now if you have a message CM, which is the message, and its length is n minus m, n and m are the dimension of the matrix, the LDPC protocol computes the syndrome S of length S and then creates the whole code, which is my message and the syndrome. And here by writing this, I mean that I am not writing the message horizontally, I am writing the message vertically as a vector. So you assume that it's a vector with each of the element as 0 or 1, classical 0 and 1. So I have my message initially, which is of length n minus m, and then I have the, actually it should be m minus m, yeah. And then I have some syndrome of length m. Okay, yeah, so the total message is m. Now, this message, the code word that we generate, it must have the property that if you multiply the matrix H with the C, the output should be 0. How do you ensure that? Because H is a fixed matrix and C, every time you might have to send a new message. You don't initially know what is C. So then you have only degree of freedom of CS, which is the syndrome. So what you will do is you will, for each message, you will choose this CS in such a way that this, when you multiply this code word to the LDPC matrix, your output should be 0. So this 0 means here it's actually a vector of length n with each element 0. Now, how do you do the coding? You need a encoding matrix. So to compute this S, you have this G of A's, which is the encoding matrix. You multiply the message with this G of A's, and you get the syndrome. Now, how do you compute the GAs then? It is very simple. Here we have split the H1 and H2 into this n minus m and m length. So here h1 is m times n minus m, and h2 is m times m matrix. It's the same matrix. I'm just writing them with giving some space in the middle. Similarly, this vector is the same vector, but I am just giving a space in the middle. And if you uh, do the math, you will see that if you multiply these two matrix and vector, it actually is equivalent to multiplying the first matrix by the first part of the vector and the second matrix with the second part of the vector, and then adding these two outcomes. And if you do some simple algebra, you take the everything to one side, and like if you multiply both of the side with h2 inverse, you will get cs. Now, implying CS equal to Atho, you will see that I did not put a minus sign here because in Boolean algebra, you don't have minus. Minus 1 is equal to plus 1. So, and minus 0 is equal to plus 0. Similarly, minus 1 is equal to plus 1. Therefore, this CS is just this number. So now, from here, I can see that if I am given the original matrix H, I can then split it up into this H2 and H1 portion. I can invert the H2 portion and then multiply it to H1 to get my encoder matrix. And this also requires that H2 must be invertible. So when you design the H originally, you have to take care of that. And then therefore this is my encoder matrix. Now this will ensure every time you have a message M, you multiply it with GAs, compute the S, construct the code word, and you will see that it satisfies all the LDPC constant. Now this syndrome CS is the syndrome. So initially we have the raw key with some error. I have the G matrix which I have computed from my LDPC matrix, and I will multiply this GH with my CM. Uh, CM to compute my syndrome. I will send this syndrome to Bob over my network using classical network, which is error free. Um, and Bob will use the syndrome and the same LDPC protocol to decode it. Now, LDPC can be decoded in many different ways. So there is no single LDPC decoding algorithm, depending on how much computational power you have. If you are using a laptop with a GPU, you can actually use certain decoding algorithm that will be able to decode the message with very small amount of syndrome, but it will take a lot of computational power. However, if you are on a mobile phone with a low-end mobile phone, you will then use more syndrome, but less computational power. So there are choices. Depending on your application, you will use the, the correct or the suitable decoding algorithm for you. Now, for example, for the binary symmetric channel, the most important algorithm is a belief propagation algorithm, which has some similarity with neural network training. But this is very computationally intensive and you don't want to do it all the time. Um, for example, a QKD protocol that generates 100,000 raw key bits will, with an error rate of 0.04, it might take 500 seconds on a 4-core Intel processor to uh, correct the errors. So even after sending a message, you have to wait 500 seconds, which is 10 minutes or 8 minutes, which is not ideal. But for QKD, you might have to because you want security there. Um, and there are this alternative decoder called a bit flipping decoder, which actually is a more of a trial and error decoder, but that's very fast and often successful. So let's briefly see how uh, this bit flipping decoder works. So I have a message and I have a code word received. I have received this code word C1 to C7 from Alice, and I want to check which of the bits are correct or incorrect. So I will multiply these two, and this I will get these equations. C1, C2, C5 equal to 0, 1, 2. And I call these equations E1, E2, E3. Now, from the matrix, even without knowing the value of the C1, C2, I can, from this equation, draw this plot where each E1 node represents a particular equation, and then all the lines are the terms that are involved in that equation. For example, E1 has C1, C3, C5. So C1, C3, and C5 are connected here. Now what you do is, when you receive that, ideally you should get 0, but if there is an error, you will get some of the equation outputting 1. Now in a bit flip error, you now randomly flip one of the bit and see whether that decreases the total number of mismatched uh, equation. If that decreases, you keep it. Then you flip another one from the remaining, and you try it several times. It looks silly, but it actually often works. And especially if you're, for example, if you had it's a constant satisfiability problem actually. So if you had a like two elements in all this equation, you would have solved it easily. Anyway, I think I will skip the code rate computation for this. However, we will look at the iterative protocol, which is very interesting. This is the last thing we will look into in this lecture. So, in an iterative cascade protocol, which is a separate protocol than LDPC, we saw how LDPC encoding works and briefly talked about decoding using this random flipping and the Tanner graph. But the cascade is very interesting. Here we have Alice and Bob. They have these messages, 8-bit message, and then one of the bits are wrong. So the 7th bit, Alice has 0 and Bob has 1. Now what Alice does is, she splits her message into two halves. Bob similarly splits his message into two halves. And then for each half, they compute the parity. So for example, in the first half, the parity is odd, so the value is 1. Second half, the parity is even, so the value is 0. Similarly, Bob computes his parity. After this, Alice sends her parity to Bob. Now, when Bob receives the parity from Alice, he notices that this yellow bit have mismatched. So Alice has said that the second block has parity 0, but I am seeing parity 1. It means I have some bit flip in my block, my second block. So now they keep the first block as it is because there is no error or no error detected. And then they split the second block again into half. And then they compute the parity. This way, whenever they split it, if the error is in one part of the split, that part will show a mismatch in the parity, but the other part will show correctness. Therefore, they can, it's a binary search, they can weed out a single error in this way. Now, if they had even number of error in a single block, this protocol would fail because even number of error will create the same parity, and then Bob will incorrectly conclude that there is no error, even though there are two errors. Um, how do you account for it? You perform the cascade once, and then you randomly shuffle all the bits. Uh, by randomly shuffle, we mean both Alice and Bob shuffle it in the same way, and then they again um, perform the cascade. Okay, so how big you should take the block? If the estimated Q bar, which is the error rate, is Q, then if you take M equal to 1 by Q, that will on average have one error. So you have this huge raw key or shifted key, and then you have 1% error. It means if you take 1/1%, that is 100-bit blocks. Each of the blocks are 100 bits. There is a good chance that each of the blocks on average will have one error. Of course, there will be some blocks with multiple errors, but then you will have to do this shuffling and correction again. So this is how you compute the total raw key total number of blocks. So if you have m is the block size, n is the total number of uh, raw key or secret key here, then this n times q becomes the number of blocks. So in the binary search, you need log 2 of m steps, because m is the block and each time you are halving it, so you need log base 2 steps, and at each step you are exposing the XOR of your block, so you are actually exposing 1 bit of information. Therefore, the total number of bit exposed during this protocol is this number. So NQ is the total number of blocks, and each block exposes this number of bits during the cascade. So you see that even though you are correcting some of the errors, you are also paying some price. You are exposing these bits. Similarly, in LDPC, they are also, when you corrected the error, you have exposed the syndrome bits. Here, this can also be considered as the syndrome cascade. So yeah, here is the failure case example. For example, if you have Alice's on the left side, she has 0 1 in the middle, but Bob has 1 0. So two of the bits got flipped. Still, the overall parity remains the same. So Bob will conclude that on the left there is no error. Okay, so when do they know that they have weed out all the error? Alice will compute a hash of the raw key and then send it to Bob, and they will match and know how this works. Um, During this protocol, they perform the both LDPC and error. They end up exposing a lot of syndrome bits or leaked information. So, and there are some eavesdropping going on, because Eve might eavesdrop a little so that you don't cross the threshold, but still she has some information. So now you need to perform a protocol called privacy amplification on this. So after the error correction, both of us have the same bit, but I know that during the error correction I have exposed some information of my bits. So I will perform the error correction, privacy amplification, to get the reduced set of bit, but the protocol will guarantee that our generated key is completely private. Okay, there are a lot of computation that goes on, but I think it's not. I think we should not cover all this. It would not be useful. So okay, we can look at this plot here. So here what it shows is, if you have on the x-axis is the m, which is the number of shifted key you have from the BB84 protocol or your protocol. Now on the y-axis is L by M. L is the number of secure key that eventually after privacy amplification you can extract. And then M is the total length. So it on the y-axis you have given a certain size of raw key or the shifted key, and given a certain error rate of that particular raw key. If you perform the error correction and everything, what is the total amount of secret key that you can extract out of it? Um, so we have skipped over those computation, but from this plot we can see that, for example, if you have an error rate of 7.5%, which is the dotted yellow line, and if you have only 10,000 bits of raw key, you cannot, even if you have corrected the error, you cannot extract any secure key, because the privacy amplification algorithm would not work on such a small, because the amount of syndrome that you expose during your error correction will be already too large, and there is no secret left between Alice and Bob in this case. So you will need larger, say more than around 100,000 bits here to get some. So for example, to get a 1% of the raw key, you need some 200,000, yeah, some 200,000 raw key bits. So 1% of 200,000 is 2,000, right? So from this 200,000 qubit exchange, you will get a 2,000 bits of secret key, and then this secret key can be used in your public key infrastructure next step. So you use that to do the AES to perform the proper uh, key key exchange. So what is the application of this QKD? You saw that even the error correction takes hundreds of seconds. So these will be used for absolutely secure scenario. If you have like $1 billion of transaction happening, you are buying some oil rig in Middle East and you want to make an online payment for that, you definitely want it to be absolutely secure. When you are controlling military equipment, you have like nuclear launch code, and then you want to transmit that to your submarine, you have to make sure that that is absolutely secure. So even waiting for 500 seconds is good enough for you to establish the secure key. So these days, all the drones and autonomous pilot, autonomous, for example, you have fleets of cars coming up. For example, Tesla autopilot programs, and they automatically update. So you are sleeping at your home, but then the central server is updating all the softwares on all the cars, and you are kind of trusting it that, oh, it's not introducing any error, or someone is not else is not interfering, and that can cause a fatal accident. So those kind of critical infrastructure will be the first target of QKD, and eventually we will optimize everything so that maybe even mobile phones would be able to do some QKD exchange. For example, when we do a trace together kind of entry, we touch our uh, trace together app. Okay. I'm told that time is up, but it is possible in future that even a mobile device would have test. You will touch it to a receptor, and they will do a QKD in fraction of a second, and we will be happy.